Good morning. 8:10, we made it, even me. So yesterday we explored the idea of classes and interfaces through the prisoner's dilemma activity, right? And so the idea is that every strategy you can envision for the prisoner's dilemma tournament concept gets embodied as a class. And each of those classes corresponds to an object that can retain a memory of what happened before. And this was one example that I had given you about how to make this work. It was this tit for tat strategy where it had a state variable saying whether the opponent had defected on the previous round. There's a way to tell it what the opponent's most recent move was, and there's a way to ask it what it has in mind. And these two methods, opponent move and is defecting, are declared in the strategy interface. And so anytime we have an object that implements that interface, it's promising implementations of these methods. So we're going to explore this particular system and application from a couple different points of view today to get a better sense of its context. First thing I'm going to go over is how these strategies are actually used in code. So this was a question that came up during the lab yesterday from one of you, and I thought it would be worthwhile to give everyone a tour of the framework in which this code is employed so that you can get a sense as to what does it mean to have a variable of an interface type and so forth. There are going to be a few details in what I show you that are a little beyond where we need to be necessarily. I might hand wave past a couple of them, but if someone feels curious about something, I'll be happy to do a deeper dive into it. So to this end, we're going to explore the simulator class this morning. So the simulator class is what we use to actually run the tournament. So if I want to test something out, I run simulator, and then boom, it gives me my results. So what happens exactly when I run it? So this is the main for the simulator class. And in this main, there are only 4 lines of code. Obviously, they invoke a lot more. But one of the goals that I want you all to be thinking about is that we try to write functions so that we can hold in our mind all at one time everything the function does. So if you've got a function that you have to scroll through 3 pages of screen to see, it's probably too long. In fact, if it isn't all on the screen at one time, it's probably too long. For that matter, even if it all fits on the screen at one time, if it's filling the screen, it may be too long. All that said, writing code, as with any writing activity, often benefits from revision. So sometimes it's best to just get the ideas down and then kind of go back later and rewrite things to make them easier to follow. So all of that said, I want to discuss the structure of this main. The first line is trying to figure out how many rounds should the tournament run. And there's a lot going on there, but suffice to say, more often than not, it's simply going to be 100. It provides a way to make it different, but that's a little beyond the scope of where we're at. Next, it creates a simulator object. So the simulator object is where the tournament will actually run. And so it uses new, so it's creating memory in the heap to store it. Here's the constructor, and it tells the constructor, here's your payoff matrix. And that too is an object of the basic payoffs class. Then, once it's created the simulator object, it tells it to run the tournament for however many rounds it figured out on this line. And then finally, it asks the simulator to print a report of what happened. And that's the whole main. Obviously, we're going to dive into these, but something I want you to appreciate about this is that in this main, you see a nice clear outline of everything that's going to happen. And I think the steps make logical sense when you think about them this way. How long are we going to go? Set up everything, tell it to go that many times, print the result. So any questions there before we start looking at how simulator objects are built and how tournaments are run? Okay, so let's look at how they're built. So I'm not going to go over every single line of the class, but I'm going to go over enough to give you a feel for how it works. Okay, so here is that constructor simulator, and it takes as a parameter an object of the payoffs type. And payoffs happens to be an interface. So what does that interface look like? It returns a score based on did the first person defect and did the second person defect. And then we have this basic payoffs class, which implements that interface, that then figures out what those payoffs are going to be. So if they both defect, they both get -5. If one defects and the other doesn't, we have the 15 and -10. And if neither defects, we have the 10s. So a lot of the goal with this kind of a setup is to separate pieces of code that don't really depend on each other into pieces that can change independently. So my simulator can work with any payoff that matches that interface. As long as I can tell it, here are the defection patterns for my two individuals, and I get a score back. How that's computed doesn't really matter to the simulator. You know, it's happy to score it however you want. And so this gives us the ability to have independently varying behaviors. By breaking up the program in this way, we make it easier to conceptualize and easier to change. So coming back to the constructor, it then calls this other constructor, which has basically some number of strategies as a parameter. And so the question is, where do those names come from? The short answer is it goes to the file system and looks in that strategies package here, which is just a directory, and finds the name of every class it can find. And that's what it processes. So then what does it do with that? It sets up some accounting stuff. So what are the scores for each name? If you want to figure out pair by pair the scores, there's a data structure that stores those. Those are both examples of what are called maps. They're kind of like dictionaries in Python. We're going to explore them in tremendous depth later in the semester. But suffice it to say, much like dictionaries in Python, they are constantly useful in practical programs. So then for each strategy, it tries to create an object of that type using this instantiate method. And if it succeeds, it then stores it in the data structures that we have available. What does that instantiate method do? That's a little beyond the scope of where we're at in the class, but put briefly, what it does is it takes the name of the class and asks the Java virtual machine, given this name, can you make me an object? You know, can you look up in your registry of classes how to create an object given this string that I got? And given that you could give it a string, which is just about anything, it might fail. You know, it's not something that can be checked at compile time. And so if it fails, there are things that it has to do. But if it succeeds, it's like, great, that's a legitimate class. So that's basically what the constructor does. From here, we go to the run tournament. And we have here a nested for loop. So basically it says, for every strategy, for every other strategy, I want them to play each other. Now, the way that that winds up working is we only want them to play each other once, but if we just do for every strategy, for every other strategy, they would actually hit each other twice, once with the alphabetically earliest one first and once with the alphabetically latest one first. So I have a little if statement here to see, do I already have a score for the two of them? And if I don't, then I go ahead and I run the contest between them. So what happens when I run a contest? That's this method right here. It takes the names of two strategies, and then it calls this instantiate method to get concrete objects of them. Now, the part here that I really want to emphasize for you all is that the data type I've declared, strategy, doesn't know the specific concrete type that you've created. So if, for example, Paxton is running this, we have Paxton 1 being created, that Paxton 1 data type doesn't appear anywhere in this block of code. All that we know is that Paxton 1 is a strategy, and it can interact with it as if it were a strategy. And the same goes for any of the strategies that any of you create. They just plug right in here. So again, this allows us to write the code to run the tournament without actually caring how it's implemented, as long as it supplies the methods that are promised in the interface. And we're going to use those methods very shortly. So as long as both of them instantiate successfully, it creates a contest object. And the contest object is where the tournament itself actually runs between those two specific individuals. So the simulator class has its responsibility, kind of top-level management, making sure that everybody gets paired off the right way. The contest class is responsible for, I have a pairing, now they need to fight it out. And so what we've done is we've delegated working that out to another object. Part of the benefit of that is the accounting that we're doing here is all handled in a method that I can really just see on one screen, so I can follow what it's doing. So it creates the contest, gives it the payoff matrix, tells it to run whatever number of rounds it asks for, and then it updates all the scores based on the result. So let's dive into what the contest is doing. So a contest object has quite a bit of data in it, actually. It has two strategies. It has scores that it's accumulating for each one, and then it has that payoff matrix. The constructor is really simple. It just initializes these data items based on what gets passed in, and of course the initial scores are both 0 because nothing is run yet. So then what happens in one round? So here is where our interface methods are finally being called. And so this round method is how you can see how progress is made. The first thing that happens is it asks each strategy, are you defecting? Are you defecting? And it makes sense that this is the first thing asked, because it can't very well tell the strategy what their opponent did on the last round until the opponent did something to tell it about. So that's the first thing we do, is we ask it, what are you doing? We then tell each of them, this is what your opponent did. So we tell one that your opponent move is whether 2 defected on this round. And then 2, your opponent move is whether 1 defected on this round. Now we ask our payoff matrix to calculate the score. And so we saw that already, but I'll refresh your memory a little bit. Here's how that gets calculated. We have those defect booleans, and then it's just a bunch of if statements to figure out the score. So finally, we've got the score, and so then we update the score variables for player 1 and player 2 based on that. Of course, that's just one round. We actually tell it to run some number of rounds. So if we come back to simulator, we see that we called the c.rounds method with the number of rounds to play. So what's that method do? It's really just a for loop where it calls round over and over a certain number of times. And that's really the simulator, and specifically you can see that's where your implementations of the methods promised in the strategy interface actually get concretely employed. That was a mouthful. Any questions? You have a question, Morgan? No. Okay. Just stretching, no problem, no problem. Any questions? All makes sense. Okay, so that's how all those pieces fit together. I'm going to change gears a little bit and jump back here to the tit for tat and talk about another important aspect of the development process that I think you're going to find pretty useful in practice. And that's the following. Way back when you were first learning arithmetic, you were taught ways to check your work. So, like if you subtract, you can check to make sure you got it right by taking the result and adding back the second value and seeing if you get the first value. So you've got ways to check your work by kind of going backwards and seeing if it makes sense. And same thing happened with division, right? You were told, well, you can check your work by multiplying back out the quotient and the divisor to see what happens. So by analogy, we have the interesting problem of how do we check our work when we write code? And at the basic level, the answer is, well, you test it. Well, that's nice. And it's true, you do. But what we really want to do is to test it without doing a lot of work. We want to test it without doing much work. What I mean by this is what we really want is to be able to write some code and basically hit one button and test it. And if the test fails, to be told immediately, the test failed. Go back and fix your code. And if the test succeeded, to get some kind of warm fuzzy back saying, it works, you did well. It's deeply satisfying to be told that. So automated testing then of the objects, the classes you create is a really, really important skill. And in a professional setting, it's expected as a matter of course that you'll be creating tests to accompany all the code you write, and importantly, that those tests run automatically. So what I'm going to do is I'm going to show you how to set up an automated test for the tit for tat class using a testing facility called JUnit. And we're going to go through all the steps of that process right here. So in general in IntelliJ, if you want to get options about something, you highlight it and you can hold down the Alt key and hit Enter. And so when I hold down the Alt key and hit Enter, it gives me some choices. It says, yeah, I can create a test, I can create a subclass, I can add Java docs, I can make package private. All of those things are interesting and important, but for today, what I care about is creating a test. So I want to create a test for this class. So now it asks me what testing library do I want? And what you want to pick is JUnit 5. Then it tells me JUnit 5 library not found in the module, and then there's this great button that says Fix. So I click it, and now it's going ahead and quickly installing JUnit 5. So JUnit 5 is now available. When you use JUnit, and you want to use the latest version, which is 5, when you use JUnit, it will create a test class to correspond to the class that you're testing. And so it came up with the creative name, tit for tat test. I'm not entirely sure how it came up with it, but I'm just going to let it go at that. So it gives it the destination package, and it even gives me an option to generate test methods automatically. I'm going to skip that for now and just kind of work on it from scratch so you can get a feel for this sort of thing. So here's the class tit for tat test. Each test method I write, I can't resolve that symbol. Okay, I want to add library JUnit 5.32 class. Okay, great. So it needed to do a little bit of configuration to make sure everything was visible. So now what I want to do is I want to create a method that's testable. So I could call it something like public void test first move. Now I need to tell it that this is a test method. And so I use this, what's called an annotation. And it turned red, so I hit Alt-Enter, and then it automatically imported for me what it needed. So this annotation tells the test system, this is one of the methods to run every time you run a test. So what happens in this method? Well, I need to create an object so that I can test something. So I'm going to create a tit for tat object like so. And now I want to test something about it. So to test something about it, I have to come up with something that can either be true or false. That is, we have to design our tests to be as simple-minded as possible. The system just wants to know, did it pass or did it fail? To that end, I provide it with what is called an assertion. So when I assert something, I am saying, I believe that if everything is going correctly, this will be true. And if I am wrong, I want you to flash red and wave your hands and get my attention. Okay, so what's that going to look like? I'll say something like the following. Assert true, and then I give it a condition. Now, the first move for tit for tat should always be to not defect, right? It's always going to cooperate the first time. So what I'm asserting to be true is, actually, you know what? I'm going to do assert false. Because what I'm asserting is that T4T.isDefecting is false. Now, if I have implemented it correctly, this test will pass. If I have not, it will fail. So, how do I run my test? Well, I go to the Run menu, and I tell it to go ahead and run my test. And then, because it's the first time I've used JUnit on this machine, it takes a while to compile. But then down here, I get my test report, and I get green check marks all the way down. That is, all my tests passed, specifically in the tit for tat test class, all my tests passed, and test first move passed. Well, I mean, that feels wonderful. It warms my heart. But to educate you all properly, you have to see what it looks like when a test fails. So we're going to make the test fail, like so. It should not be true that it's defecting, right? So at this point, the test is erroneous. So now I'm going to run it again. And as I run it, okay, it did not pass. So I get these yellow X's here. And then down here, it gives me a report about what happened. And it tells me that the expected value here was true, but the actual value was false. Then it'll say, click to see difference. Click to see difference isn't terribly useful with Booleans. Where it's really useful is with stuff like strings, where it'll put the string that you expected and the string that you got side by side, and you can see exactly where they were different from each other. And that can be really, really useful when you're writing a test. I mean, if I click on it here, you know, I've got expected is true and actual is false. So you at least see what it looks like. Not terribly interesting with a Boolean. But yeah, like I said, with strings, it's phenomenal. So I'm going to close that. And now, of course, you know, I'm a perfectionist and I really, really want my test to pass. So I'm going to change it back and I'm going to run it again. And bam, now it's passing. So I have a passing test. My question for you all is this. Does it mean that my code works perfectly? Why not, Graham?
Because it could run fine, it just might not do exactly what you want it to do.
Okay, and what else do I want tit for tat to do? What other, so I tested its first move. what other aspects of tit for tatness might I need to test?
It changes based on what the opponent does.
If it changes based on what the opponent does. So we're going to write another test to see if we can examine that. So at test and public void test if I'm going to call it test revenge. So there are different ways it can change its behavior depending on what the opponent does. What I'll do for starters is test, can it take vengeance upon the foe? So let's see what that looks like. I'm going to create a tit for tat object as I did before. And now what I'm going to do is I'm going to tell this poor thing that your opponent move is to defect. So that's what your opponent did last round. Now I need to assert true t for t dot is defecting. So if you look up here or read carefully, notice it's just running tit for tat test dot test first move. I really want to run all the test methods. So I'm going to highlight that, the name of the class, and then it creates this option, run tit for tat test. And so that means it'll run all of the tests in that class. And so this time it ran both tests, and we got that test revenge passed, and test first move also passed. You always want to run all your tests. Part of the reason for this is as we are modifying our code and fixing occasional errors that may or may not crop up, some of you may create error-free code the first time. If so, that's great, and I want you to keep doing that. For the rest of us who don't create error-free code the first time, we want to run all our tests. So I've tested revenge. So now I want to test if I got revenge on it and then it cleaned up its act. Did tit for tat forgive it? Right. So I'm going to call this test forgiveness. And what I'll do is I will tell it that its opponent defected. And then what I'm going to do is I'm going to tell it that its opponent cooperated on the turn after that. And then I will assert false for t dot is defecting. And now I'm going to run tit for tat test again. And it passes. So these methods together really do represent a fairly complete description of what tit for tat ought to do. Tit for tat, admittedly, is an extremely simple program. Let's talk about some things I am not able to do. In general, tit for tat is a relatively straightforward case, but even so, not super straightforward. We're going to talk about that in a moment. In general, I cannot test every possible input. I cannot be expected to write tests for all possible inputs. Let's think about what that means in this context. How many possible inputs are there for tit for tat? What are they? Okay. So I'm going to push back on this a little bit. True and false are the only possible values for the opponent move method. But I would argue 2 calls to opponent move is a distinct input from 10 calls to opponent move. That is, when we think about what's the input, one of the inputs is what state was the object in before the current method call changed its state. So what we actually find is that the total number of possible inputs, so let's let n be the number of rounds, right? So for the first round, we have two possibilities. For the second round, we have two possibilities. And then we get to the last round. So we have 2 to the n possibilities, given a number of rounds. Now, knowing what we know about my implementation of tit for tat, this really doesn't matter very much. By which I mean, the implementation is itself so totally simple. That is, it only retains as history the previous round, that knowing about that implementation, I can be quite confident in these tests, that these tests are comprehensive. But what I really want you to think about is the fact that these tests are implementation independent. That is, there are all kinds of ways I could implement it. I could have some crazy array thing going on, who knows, right? And for some space of those implementations, the behavior really could vary depending on how many rounds preceded us. And so it's in that sense that we have 2 to the n distinct possible inputs. The overall point I'm making here is that if you have an object that changes its state over time, the total number of possible inputs depends on how many times can you make its state change. In other words, how many times is it possible for something external to the object to cause it to change something? In general, would you all think that we're even able to place an upper bound on that? Absolutely not, right? So in fact, the space of possible inputs isn't just absurdly large, which is what 2 to the n is. It's actually infinite, which is really absurd. The point of all of this being, even in theory, even with a pretty simple program like this, you are not going to be creating a completely comprehensive set of tests. Even if you could, there are probably so many of them that running them would just take too long, which is annoying, but there it is. In practice, how do people deal with this? The number one thing we like to think about are, what are the cases where what we expect of its behavior will change? You know, what are like the critical inputs that trigger different kinds of behaviors? We also think about things like, in general, what are some borderline inputs? For instance, you can think of test first move as an example of a borderline input. We haven't even done anything to it. Let's just make sure it's starting right. You know, often if you've got integer parameters that do different things at different boundaries, it's good to write tests at those boundaries and see what it does. So that's one kind of family of strategies. Another family of strategies is what is called fuzzing. And we're going to talk more about this later in the semester, but I want to introduce the basic idea now. The idea of fuzzing is, given that you've got this vast space of possible inputs, you can write tests that pick random inputs to test it. So in effect, what you're doing is a statistical sample of the space of possible inputs to see how the system performs in general, to get a feel for how it does. Fuzzing is complementary to the method I was just describing of thinking carefully about what are the circumstances that cause it to change. It's important to use complementary strategies because each has strengths and weaknesses. The strength of fuzzing is to get a nice representative sample of inputs. Its weakness is that it's not really going for the weak spots, you know? The strategy I looked at here really is going for the weak spots, but it misses a lot of possible inputs, you know? And so working together with these different strategies, you can often create a really nice test, Of course, the trick with fuzzing is that for any of those random situations, you have to know what the correct behavior is. which often requires thinking really, really carefully about the system. For now, I encourage you to mainly think in terms of specific tests that identify important ways that the system changes. And I wouldn't worry much about fuzzing at this point. But I'm going to talk about it later in the semester in more detail. And it'll be something I do want you to think about later on. For this specific assignment, I'm not going to require that you create tests, but I am going to strongly encourage it. The reason being, if you get in the habit early of writing tests for all your code, I think what you're going to find is it's actually kind of addictive in a good way. That is, every time you write some code, it's like, did it work? Often when we write code, we write it and then we can have one of two mindsets. One mindset is, this code, I've written it. Whether or not it works is sort of a mystery, and I'm not really going to think about it anymore. Here's another mindset, equally foolish. I wrote this code and my feelings are really going to be hurt if it doesn't work. So I don't really want to test it. Or if I do, I don't want to test it too much, because I prefer to live in this reality where my code works the first time without having to test it. The reason I can speak so eloquently of those mindsets is because I myself know them well from the inside. Writing your own automated tests from the outset is a way to splash cold water on yourself and make sure that the dumb thing works. Furthermore, writing tests is an incentive to keep your methods relatively small. By writing lots of small methods, you can test each of them independently. That in turn helps you quickly figure out where the bugs are if something goes awry. So that too is a benefit of having a companion test class for each class that you're writing. It can be pretty handy. Depending on the circumstances, you could even imagine writing a test class to accompany an interface. That is, there might be certain things you expect of anybody implementing the interface. And so you can write some tests to make sure that for lots of different implementations of the interface that it does the right thing. That kind of thing. Cool. Any questions about this? Any questions? Test early, test often. It takes a little more work to code this way. This case is not so unusual in that the amount of code I wrote for the test actually wound up exceeding the amount of code I wrote for the implementation. That happens from time to time, and it's okay. It's okay to do that. Sometimes it's just what you have to do to be able to talk about what the system is supposed to be doing. Cool. Any questions on that? So for the last 10 minutes of class today then, let's play with arrays a bit. I know a number of you have found arrays in Java to be confusing on multiple levels.
I find strings confusing.
Okay. We will hang on to that idea. If we don't get to strings today, we will totally talk about them on Friday. We're going to start with arrays. Part of why arrays are confusing in Java is that Java doesn't provide a lot of the cool, concise syntax that Python does for thinking about them. So the list in Python is the rough equivalent of the array in Java. But here's another big difference between them. When you created a list in Python, you didn't have to say how big it was at the beginning. You do have to do that with arrays in Java. Now you might be wondering, why? Why do they bind us in advance to committing that the array is only going to be this big and no bigger? And how do we deal with this? The second part, how do we deal with this? We're going to cover that. We're going to start covering that maybe towards the end of class on Friday and absolutely on Monday. We're going to see some concrete ways to deal with it. In fact, we're going to be looking at how do you take a fixed size array and make it a flexible array as our first data structure of the semester. Our first data structure will be the resizable array, which is what the list in Python represents. So why do we have to start with a fixed size? It goes back to thinking about what the computer is physically and how the idea of an array corresponds to that. So we talked last time about the main memory of the computer being really, really large, like potentially billions or trillions of bytes, right? Those bytes, each of those bytes has a unique memory address. That memory address is an integer. By analogy, you can imagine that all memory locations in the computer are in a single giant neighborhood with a single long street taking you all the way down. Actually, my neighborhood kind of looks like that. It's a single long street, and then it's got a couple cul-de-sacs off the side. So forget the cul-de-sacs. Just imagine a single long street. A what?
And nothing, it looks like a club.
Oh, yeah. So you got a single long street, and the address, when we say the memory address, what we mean is literally like a house address. What's the number where you can find it? So our addresses, of course, start at 0, and then we have 1. They go up by 1 every time, unlike addresses in most neighborhoods for some strange reason. My own neighborhood has like 50 houses, and our addresses are 4 digits long. Why? Why 10,000 possibilities? It's beyond me. Anyway, getting back to the matter at hand, we've got these addresses in memory. 0, 1, 2, 3, 4, 5, all the way down to, a billion or whatever, okay? And a premise that I'm just asking you to accept for the purposes of this class is that the computer hardware, the circuitry from which the computer is made, lets us extremely quickly find a value or change a value at any of these addresses. So if I say I need to look at address 10,000, the computer's hardware can get me that value or change that value without looking at 0 through 999, well, however many. It can do that, no problem. Okay, and it'll do it extremely quickly. So, given that premise, an array is a view of a sequence of these addresses. Let's say I create a 3-element array. So I say something like int a equals new int 3. Something like that. And for now, we're going to pretend that ints are only 1 byte in size. They're actually 4 bytes, but we're going to hand wave past them. Okay? So what the operating system does is it explores the memory of the computer and tries to find 3 consecutive memory locations that aren't currently reserved. So let's say that one's in use, that one's in use, but these 3 are available. So it grabs those 3. So this is what new is doing. So it grabs those 3 addresses and says, these 3 addresses belong to A. They are A's property, so to speak. Okay? Now, what happens if I do an access like A bracket 1? What happens is it knows that A starts at memory location 2. So it'll take that 2, which is A, and add a 1, which is my index, giving the address 3, which is right there. So an array lookup simply requires an addition. It may also require a multiplication. And then it just does a memory access. So the idea of the fixed size array is an extremely transparent view of the hardware giving us the memory. So why the fixed size? Well, when I ask the operating system to reserve some memory for me, let's just say it would be obnoxious to ask the operating system to reserve all remaining unclaimed memory. What possible drawbacks might a scheme like that have?
There's no memory for a future work.
That's right. If I want my array to just be as big as it could ever be, right? And I say, okay, operating system, give me all the bytes. All the bytes belong to me. Then, if I try to ever create another object, there's nowhere to create it. Why? Because my greedy array took all the bytes. So, fixed size arrays are one of the most fundamental data structures because they're just a thin abstraction on top of the physical memory that the computer provides. That's all they are. That's all they are. Cool. Any questions about that? Any questions? None there. Okay. So let's see. I think we'll call it a day on that. That's a good stopping point. So on Friday, we're going to talk about arrays and strings some more. And also, if you have any questions about anything between now and then, bring your questions to class. I'll be happy to go over whatever you need. I'll see you all Friday.